We perhaps have a quorum here now. We can get started. Last 5 lectures we have concentrated on classical theory of Siegel modular forms. The first lecture we just did basic definitions and basic notations and so on. Then we looked at examples. Then it was the turn to discuss Hecke theory and L functions. And the final 2 days, 4th and 5th lecture, we looked at lots of results in current areas of research, and everything that was being talked about was talked in the classical language. So you can spend your whole life just doing that, and it's perfectly fine. There are lots of examples of people who are extremely successful doing that. But for at least the students here and the senior people too, it is always a benefit to learn as much as possible while you are a student or a postdoc, and maybe it is applicable to your thesis problem or not, but certainly it gets used sometime in the future. So part 2 of the workshop is the automorphic representation part of the story, and we'll spend the whole lecture today starting from a Siegel modular form, constructing a function, C-valued function on the group of adels, then seeing what kind of function we get, what nice properties we get just because we started from a Siegel modular form. Then we will see that there is a standard way to define a representation, and because you started from a Siegel modular form, the representation is a very nice object, and it breaks up into local representations and we can describe them completely. So the final theorem would be, I have a Siegel modular form, I got this function, I got the representation, these are the local components, every single detail. Okay. So along the way you will learn, we will learn lots of standard stuff, and let me also tell you, we are doing this in the context of Siegel modular forms. This paradigm works very well in other situations too. So in a certain sense, this is also, if you looked at the GL2 notes that we had for the automorphic part, what we are going to do today is essentially point by point follow that, but look for GSP2n now. Okay. So let us start with classical to adelic. So what I am going to do now is I am going to denote this by G, okay, not GN or G2n or whatever, because I am going to have to write GSP2n a million times. I am going to write as less as possible. I am going to write G, and when I have to reduce to genus 2 or something, I will say, oh, by the way, now I am talking about genus 2, now I am back to general genus, but this is my abbreviation, and I want to start with f in sk gamma n, and I want to define a function phi f on the adels to C. Okay. So now the intuitive idea is the following. This guy is a function from Hn to C. So you look at the Siegel upper half plane, and how do you get the Siegel upper half plane? You take any matrix G in G infinity plus, so G infinity is G of R, so GSP2n R, and your Z can be written as G1n. Okay. For every Z you can get a G, and I am going to also abbreviate this as a capital I. Capital I is square root of -1 multiplied by identity. Of course, many such G give you the same Z, and the stabilizer of this point is exactly your K infinity, stabilizer of I. So basically K I is equal to I, and this is exactly those matrices x, y, minus y, x that we had looked at. Okay. So essentially, if I want a function on, I have a function on Hn and I want to somehow go to the group, I have to define it on G infinity mod K infinity. Okay, because this is my Siegel upper half plane. But on the other hand, I just don't want random function, I want some special property with the gamma n, right, some automorphic condition. So gamma n is what? G of z. Well, G of z is exactly, you take any rational matrix and you are telling me that even though you took a rational matrix, there are no denominators. That is basically saying G of z, which means for every prime p, this actually is in G of ZP. For every prime P, it's a integer. So, in fact, your discrete subgroup here is, so this is P less than infinity. P equal infinity is your R, and for P less than infinity is your periodic field QP. So, basically, if I want some kind of a property on gamma n, I want the GQ and the product GZP to be kind of quotiented out. In a certain sense, what this tells us is, look at the following. So, write GA as rational matrices on the left, G infinity plus in the middle, and product GZP on the right. Given any such element G in here, write this as G equals gamma G infinity K, and define phi f of G to be equal to f acting on I. So, you notice when I wrote with this slash operator, I drew two slashes. Earlier I had only one slash. So, this is related to the previous one by just a factor of the similitude. So, this is mu of G to the n k over 2 j g z to the minus k f of g z.
So, no determinant G there will be.
Of course, there is a determinant. Thank you. This doesn't make sense without a determinant. Yeah. So, basically you can see that your previous slash is this new slash times some power n k by 2 minus n plus 1 by 2 f double slash k g. And reason for now introducing this is not just to make your life more complicated by introducing more notation. The idea is that the single slash operator that we defined earlier was very convenient to do the classical Hecke theory and get very nice formulas for the Dirichlet series in terms of the L functions and so on, these theorems of Andrianov. Whereas now, if I write down the slash operator with just this power of mu, we are going to check that this function is trivial on the center. So, we want it to be trivial on the center. That is the reason why we are modifying this. Okay. So, of course, the first question is, I write this as gamma G infinity k, you write it as gamma prime G infinity prime k prime. Do we get the same thing? So, well definedness, and this is our first exercise. So, several of these exercises are very basic, but they will give you very good experience in manipulating these adelic things and so on. So, it is a very instructive exercise. I really strongly suggest that you take these initial ones very seriously, because they will familiarize you with these adels and the rationals and how these things sit inside. Okay? So, pay close attention. Okay, so, given an f, I have defined a phi f, it is a function on GA, and I am going to start writing down its properties. Okay? Property of phi. So, this map f goes to phi f. Well, let me just write it this way. Properties of phi f. Number one, there are some obvious properties which come from the actual definition. Because it depends only on G infinity, my function is left invariant under GQ and right invariant under the compact, just by definition, because if I multiply something, they get just absorbed. So, number one is phi f gamma G equals phi f of G for all gamma in GQ. And this is one of the most important defining property of a automorphic form on the adelic group. It is a C-valued function on the adelic group which is left invariant under the rationals. So, just by simple writing down the definition, we automatically got this automorphic condition right here. Okay. Second is phi of f g k 0 is equal to phi of f g for all k 0 in capital K 0, where capital K 0 is exactly what we have on the right there, product p less than infinity of k p, where k p is your maximal compact in G p. Okay. So, there is some very nice right invariance with respect to all of these groups k p, all of them put together. Okay. Now, another thing that needs to be figured out is, well, inside G infinity, I have k infinity, right? This guy right here. What happens if I multiply on the right by k infinity? Well, it will do something with the slash action. K infinity on I does nothing because that's the definition of K infinity, and just the J part comes out. Okay, so right invariance with K infinity is also something that we can write down. There's a typo, I missed that. K infinity I to the minus K phi of G for all K infinity in K infinity. This is of course true for all G in G. I'm not writing that down. Okay, then I said that with the center things are going to look good. So what is the center in here? The center is given by, so center of G is, unfortunately the notation for the center is Z, and these are scalar matrices, okay. And what happens is, if I have such a matrix, say I have alpha, 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 then you should look at what happens here. The real part of that alpha, alpha, alpha will come in here. Then you have the alpha, alpha, alpha here. The similitude in that case is alpha squared. So you get alpha to the nk out of this. The Cz plus Z, the D part is just a n by n alpha alpha matrix. Its determinant is alpha to the n, k cancels out. So this is the reason why we defined it with the nk by 2. If we did not have the nk by 2, we will have something complicated coming out. We don't want that. So trivial on the center, phi f zg equals phi of fg for all z in the center. Okay, so far looking at just the definition, we can glean out these 4 very basic properties. Okay, any questions?
Oh, wait, I'm sorry. Is Z inside the stabilizer of I? I mean, sorry, is the center inside the stabilizer of I?
Say that again.
The centralizer, which you call Z, is that in the stabilizer of I?
No, because these guys are x, y minus y x with x, x transpose plus y, y transpose equals identity. But I won't get identity if I have just a diagonal, right? I'll get identity times alpha squared.
Okay, so in the GL2 case, I think the center does the center does stabilize the I, right?
Center does stabilize. Yeah, you're right. Absolutely. Sorry. Yeah, you're absolutely right. So the Archimedean part is all real numbers alpha, and of course A, Z, D inverse is alpha on one side, alpha inverse on the other. Yeah, it stabilizes. Sorry.
Okay, so K infinity, does that contains the center then?
Yes, K infinity does contain the center. You're right. So you can put in the K infinity. Yeah, so when I write the stabilizer, I should write this as maybe Z infinity, K infinity. You're right.
Absolutely right. Okay, in that case, what's the definition of K infinity?
K infinity is this guy. Or, so this is isomorphic in this case to un, so that's the K infinity in this case, yeah. Good, yeah, so K infinity is the K we saw earlier. Good to put our feet on the ground and have everything clear. Okay, so we know something more about our modular form here, namely that it is cuspidal. We haven't used the cuspidality and we haven't even seen the Fourier coefficients appear anywhere here. So how does the cuspidality work out? So this is going to be a lemma, and this says that if f is a cusp form, then phi f is also a cusp form, i.e. for the unipotent radical of every proper parabolic. I know these are lots of words. I'm going to tell you the genus 2 examples in a second. So unipotent radical n of every parabolic subgroup of G, you try to find the constant term. You take phi f n g dn. For example, if you had a modular form of genus 1 and you have summation a n e to the 2 pi I n z, you get a0 by integrating from 0 to 1 f of z plus x dx. That's what gives you the constant term. How do you get z plus x? You take z and you act on it by 1x 0 1. these upper triangular matrices. These are your unipotents right there. So instead of doing this in the very simplest case, you take every unipotent radical of every proper parabolic and you want this to be equal to 0. And the idea here, so maybe I can just give you at least a feel for how these things look like for genus 2. There are 3 proper parabolics, and we'll get to the explicit definition of these guys in the next lecture. So there is a Borel. This corresponds to the upper triangular matrices in GLN, and in this case your radical is given by 1 1 1 1 star 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 star. Remember, we don't really have upper triangular, but we have these things going on because of the way our GSP4 is defined. So this is the Borel. Then there is the Siegel parabolic, which we have been secretly seeing all the time anyway, X with X equals X transpose, these 2 by 2 matrices. And then when we define the Klingon parabolic, we in fact use when we define the Klingon Eisenstein series, we were using the Klingon parabolic. And in that case, the unipotent is something in between these 2 guys. So it is, so a star here and a star here, star, star, star. So what this lemma says that you have to check for all these 3 cases that when you do this integral, so you take constant term for every parabolic, and that has to be 0. That is a definition of being a cuspidal automorphic form. And the way you do this is actually quite nice and not so hard. I didn't want to spend the time here, I'll just give you an idea. So what you do is basically you look at the intersection of all of these guys, and you can see the intersection is identity star 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 0. That's the intersection, right? That guy is in here, here as well as here. In general, if you look at GSP2n and look at every proper parabolic and the intersection of the unipotents, then it looks exactly like this. Identity n by n symmetric matrix where only the last column and last row are non-zero. So that's the general case in the general genus n. And what do you do if you try to integrate on this guy? You basically change this integral over the real part of this group, then using phi f of g is related to g infinity, you bring down the integral into an integral involving the modular form. Then you replace the modular form by its Fourier expansion, and then you use the fact that your modular form was cuspidal to get 0 for these integrals. So I said too many things too quickly, but that's basically how the cuspidality of f plays into the cuspidality here. Let me write down number 5. Phi f is a cusp form. So I wanted to put this as an exercise, but instead I thought, well, let us do something a little better. So I wanted to tell you how you can define adelic Fourier coefficient in the most natural way, and it relates with a very easy formula to the Fourier coefficients of your f. So for example, what you can do is you get the constant term by integrating. So if you have f of z equals summation a n e to the 2 pi I n z n equals 0 to infinity, your a0 is 0 to 1 f of z plus x dx. But if you want to do any other n bigger than 0, then a n is 0 to 1 f of z plus x e to the minus nx dx. So you have to look at the inverse of the character coming from the integer n, and of course when n is 0 you get the previous one. So now if you want other Fourier coefficients, you don't just take this integral, but inverse of a suitable character corresponding to your Fourier coefficient. So that is our.
You mean here 2 pi I x e to the power minus 1?
Yes, 2 pi I. Sorry, you need the 2 pi I. Yeah. So basically, this is part of the exercise, and I can just mention that any characters of NA are in 1-to-1 correspondence with, so let us maybe, to have our life simpler, still continue the n equals 2 case. So this is in 2 by 2 symmetric matrices which are rational. So when you do the Fourier analysis for adelic points, you get rational points as parameterizing the character, and you can see that the Fourier expansion of your Siegel modular form is parameterized by 2 by 2 symmetric matrices, but which are positive, definite and half integral. So if you take S and a corresponding character theta s, and you define adelic Fourier coefficient where you integrate over the same space phi f n g theta s inverse n dn, then our exercise, which is a very instructive, useful exercise, tells us that this is actually equal to a of s e to the minus 2 pi s if s bigger than 0, half integral, and 0 otherwise. So it completely gets related, the adelic Fourier coefficient gets related to the classical one, and this kind of computation is very useful. For example, in a recent paper we were trying to figure out what these for the Saito-Kurokawa lift, what do these mass relations mean. So Saito-Kurokawa lifts already in the 70s were completely understood in a representation theoretic way. How do you get all of them using theta lifts and so on, but there was absolutely no explanation of what does this recurrence relation amongst Fourier coefficients means in the automorphic setting. So in a recent paper with Ralph and Abhishek, we were able to show that if you have a Saito-Kurokawa lift, you know that classically that the Fourier coefficients have a recurrence relation. So what did we do? We took a Saito-Kurokawa lift and we took it coming from the automorphic side, and we said, oh, if that is the case, then the representation theory tells us something about how the representation looks like, and then we can look at what's called the Bessel model of such representations. We're going to talk about Bessel model in the next couple of lectures, and then it turns out that if you have a Saito-Kurokawa lift, you get a very special kind of representation locally. And in that very special case, the Bessel model, these are just functions on your GSP 4QP, satisfy a local recurrence relation. And these local recurrence relations together as a product give you the recurrence relations on the Fourier coefficient. So somehow this automorphic explanation of mass result, this was just a curiosity for us, and it turned out that it depended on a completely local representation theory Bessel model question. So it was a very intriguing problem and a very satisfying answer, but the crucial thing was to relate these guys. I mean, how do you go from the Fourier coefficient or the automorphic form to Fourier coefficient? You have to do something like this, and that's the important thing. So we will see that maybe in the future lecture. So what you have so far, I have to start erasing things, so I want to summarize before I do that. We defined a function on the adelic points g of a. We defined it in the most natural way by seeing what the groups look like and what does the Siegel upper half plane mean with respect to the group and so on. We have a nice decomposition of g of a, and it naturally gives us something. As soon as we write down the definition, the first 4 properties were sort of free, just reading out of the definition. So that those 4 properties are, by the way, true for any Siegel modular form, nothing about cuspidal, but as soon as you assume cuspidal, you can show that your function on g of a also satisfies the definition of being cuspidal, namely the integral over every unipotent radical is 0. So you are actually the going is very good so far, because we are getting exactly all things that we actually need to create cuspidal automorphic representations. Okay, so this is the story so far. I'm going to do anything more, I need more information on F. And the next thing that you have is that you assume a Hecke eigenform. And that's what we're going to look at next. Hecke eigenform here means what about phi of F? Before we do that, any questions?
Yes. Have you defined the word automorphic form yet?
I'm not going to define.
You accidentally said it a little while ago. Okay.
Yeah, so the definition of automorphic forms is ultimately I'm going to have a list of lots of things. That's it. Yeah.
But is that the entire list? Maybe?
Not yet, yeah. In fact, automorphic form is left invariant with some growth condition and some, you know the definition, right? But the actual formal definition for a group, it's not required. We're not going into it. But you're right. I'm talking about things, and I'm not talking about them as well. Yeah. You had a question?
So this is the definition of cuspidal form, right? Cusp form.
Yes, this IE is actually the definition of a function being a cusp form. Yeah.
So means is there any alternate definition regarding the Fourier coefficient? Like here you obtain the Fourier coefficient.
So in general, when you're looking at functions on the group of adels, this is what you mean by getting a cusp form, and ultimately when you create a representation, you get cuspidal representations out of something like this. And the way you get this in this situation is by relating it to Fourier coefficients of your f, and then the reason that this thing works out is because your Fourier coefficients are only supported on positive definite matrices. So there's no point in me writing down an alternative thing. My alternative definition would be that f is a cusp form. I mean, it would be a tautology. Phi f is if f is a cusp form, then phi f is a cusp form if f is a cusp form. So, but ultimately that's the proof. That's the proof that you have.
And why did we look at the intersection? Like, is it enough to look at the intersection to figure out whether it's a cusp form?
So if you think about it this way, you are integrating on a group, and you take a subgroup, and then you do an integral on the subgroup, inside integral on the subgroup, and then an outside integral on big group modulo subgroup. If the inside integral is 0, the whole thing is 0. So that's the reason why you can zoom in on the smallest part which is common to everything. I don't want to do one integral for every parabolic. So I do it all in one go by looking at the intersection. And that's a very good question. Why did we do that? Because I can take care of every single parabolic in one go.
And also, is there a trace S there in the Fourier coefficients, or?
Yes. Trace. In fact, what we can do is we already have a Peterson inner product on our cusp forms here, and we can define these functions that we got now are from properties 1 and 4. These are functions on g of a modulo g of q and the center. And so you can you have a inner product on the L2 space, L2 functions of this space, and you can basically see that whatever inner product that you have for f1 and f2, it matches with phi f1, phi f2. So I'm going to write it down here and not write down the actual definition. I have left it as an exercise, and it's a simple exercise that f1, f2 is phi f1, phi f2. And what you have to do here basically is to make sure you understand what measures you are using and everything. But I don't want to write down these details. This is just simple bookkeeping. So in the exercise, I kind of introduced the definition of the right hand side and tell you what it means that something is equal. And then you can very easily see that this definition here of phi of f in terms of f gives the equivalence of the norms in a very simple way. So 2 lines proof really, as soon as you figure out the definitions. So this is a pretty good map, f going to phi f, and now we want to see what happens if you have Hecke eigenform. So the Hecke algebra in the classical case, we had to work quite hard to define it, double cosets and slash action, and product is some complicated product, symplectic divisors and so on. Whereas in the group situation, defining the say the local Hecke algebra is actually very simple, and it goes this following way. So basically you have your GP. This is now local, P is a prime, because we are our Hecke operators anyway that we looked at were for all primes, and then they put together, they give us the whole Hecke algebra. So one prime at a time is good. So this is G of QP, and KP is G of ZP. And I want to define the Hecke algebra H GP comma KP, and this is the space of compactly supported functions T from GP to C such that P K1 G K2 is T of G for all K1, K2 and KP. So compactly supported and left and right invariant with respect to the maximal compact. And so you can see it was very easy to write down. I did not have to do any formal sums and then gamma and invariance and so on. These are actually C-valued functions, and you can also see very quickly that they are invariant on the left by Kp and on the right by Kp as well. So they take constant values on Kp, G, Kp, right? And Kp, G, Kp is a compact set because Kp is compact. But since the function is compactly supported, it's non-zero only on finitely many of these. So immediately you can see that this is generated by characteristic functions of Kp, Gkp with G in Gp. So you can see actually that these elements of Hecke algebra are indeed finite linear combinations of characteristic functions of Kp, Gkp, which is very much like the Hecke algebra classical thing that we had was any element can be written as a finite linear combination of gamma n, G gamma n. So this is very much in parallel here. But of course, so far we didn't define any product, and the product in this case is the convolution product. In a certain sense, the product that we had for the classical was also a convolution product in secret, but we did not write it like that. So if you have T1, T2 in H, Gp, Kp, then you define T1, T2 of x, product over Gp, T1 xy, T2 y inverse dy. So you are integrating over the whole space Gp, but both these functions are compactly supported. So the convergence is not an issue at all. It's a very nice object that we have here. Okay, so with this product, you can check that if you do the convolution, and if you want to check that this new function is also satisfying this property. So if you multiply x on the left by a k1, the k1 is coming here, but it gets absorbed by the t. If you do it on the right, so k2 goes here, you do a change of variable, it becomes y inverse k2 inverse. It goes off on the right. So this new function is also satisfying the crucial property, and of course because these two functions are compactly supported, this one is as well. So it's naturally sitting inside your Hecke. Now we can call it Hecke algebra because now we have defined the product as well. So it turns out, I mean, all the things that we are doing are completely in parallel to the classical stuff. So it turns out that you can actually have, so your classical Hecke algebra is isomorphic to our thing right here. And the way you see this is, well, what is H and P? It's all double cosets gamma n, G gamma n, where G has similitude power of the prime P. And with a little bit of a thought, you can see that actually this comes from, so I know when we are looking at gamma n, G gamma n, we wanted G to have integer entries and prime power similitude, but now I can slightly modify this and I can allow denominators which are only powers of this prime P and look at gamma n on left and right. So this modification, of course, it's not exactly the same, moves us away from what we did classically, namely integer matrices, but you can with a little thought realize that this is also giving you the classical local Hecke algebra. And this thing as a set you can show is actually isomorphic to Gp, because basically how do you get G of Qp? You take this guy and you look at its completion. Okay, the completion of this is exactly your Qp. So you get Gp here, and on this side you get Kp, on this side you get Kp, the groups right here. So the p-adic completion gives you, this guy gives you this, and gamma n actually give you just GSP4, GSP2 and ZP. So these guys are generated by elements of this kind, these guys are generated by elements of this kind, both these sets are the same, so these Hecke algebras are also same. So in a certain sense, when we are going to apply Hecke operators, we will move from one space to other depending on the context. And then we will say, oh, I am applying this on the classical guy, and then I apply the corresponding one to the automorphic guy. And by corresponding, I would mean by this correspondence.
What's the unit there?
Yeah?
The multiplicative unit?
Multiplicative unit is probably the characteristic function of Kp. Yeah, just Kp, G equals 1. Okay, so now how does, we know how the classical Hecke algebra acts on classical Siegel modular forms. How does the p-adic Hecke algebra act on automorphic functions? You'll see that what I'm going to write down is very much like what we did in the classical case. So what we'll do is take M in Gp, and let t be equal to characteristic function of kp m kp. Okay, and I want to define the action of t on a function phi satisfying these properties. Okay, so I'm not going to write phi sub f. I'm going to take any function phi which satisfies these properties, and the way you do it is, well, you will see already the first step is very similar. Disjoint union mi. Instead of right cosets for the classical case, I'm looking at the left cosets, and you will see in a second why I took left cosets. Hold on. So to define this, I don't even need the coset decomposition. The definition is just integrate over all of gp, t of h, phi of gh, dh. T is a function on gp, phi is a function of all adels, but you can think of it restricted to gp as well, and so you can define it this way. So this is just a random definition. It looks completely different now from the classical one, but as soon as I do this kind of decomposition, what would happen? So when I'm integrating this, it's a characteristic function of kp m kp. So in this integral, t of h is equal to 1 when you are over kp m kp. But kp m kp is the disjoint union of these guys. So this thing ends up being summation over I integral mi kp of phi of g mi k dk. Right, because I am integrating over kp m kp, t of h is equal to 1. Kp m kp is a finite disjoint union, so it breaks up into a finite sum of integrals. But what about phi property number 2? If I multiply on the right by kp elements, it's gone. So this function that I have here is independent of k, it just comes out, and all I get is an integral of kp. So basically you normalize your measure on gp such that the volume of the compact is 1, and so this ends up being summation I phi of gmi. So now it feels a little familiar, right? It was in the classical case you exactly had the if gamma n g gamma n was union of gamma n gi, then the action was summation over I f slash k gi. Well, this is exactly looking like that, and now you see also the reason why I took left cosets, because my function has some very nice property with respect to the compact on the right. I wanted to get rid of it. If I took right cosets, I wouldn't be able to do anything. There will be a g here, a k and a mi, and the k will just be sitting there, and I won't be able to move it out.
There will be major.
Yes, so that's exactly right. So the measure, so I would this thing will come out, and then the integral of this set dk, and then you normalize it so that the integral of the volume of the compact is 1. So there is a normalization of the measure that's happening here. You're absolutely right, and that's a very standard normalization. You define the Haar measure on gp such that the integral volume of kp is just 1. Okay, so I have the action of Hecke operators on Siegel modular forms. I now have action of Hecke operators on the automorphic forms as well, and the question is, are these two actions compatible? Because you see, any of my t here can act on this guy, but this belongs here. There is a corresponding guy here which acts on a Siegel modular form. So the question is, I take a Siegel modular form, get the automorphic form there, apply the Hecke operator and get something, or I take a Siegel modular form, apply the Hecke operator and then corresponding automorphic guy. So do I get the same thing whatever I do? And of course the answer is going to be yes, right? Otherwise, what's the point? What is the point if nice things don't happen? But for the matching to happen, I know when we defined the classical action of Hecke operator, we did it with the slash k. But now going from f to phi f, we have this double slash k, right? So we have to define this modified action of the Hecke operator. So if I have gamma n, m gamma n, mi prime, and I define, so this is my t, so t double slash k of f is defined as sum over f double slash k mi. and we basically see that this is mu of m n times n plus 1 minus k over 2 of my classical action. It's just the factor of mu. So it's just a constant times. As soon as I fix my m, it's just a constant times this thing. And so I get my property number 7. That, how should I write this? T phi f is phi t double slash k f. And the idea is, how do you prove this? Actually something that we have already done. Okay? Here you have left cosets, here you have right cosets. And we did an interplay between left and right cosets when we showed that the classical Hecke operator Tg was self-adjoint. Inner product, we did this mu mi inverse, and you went from the one side to the other side, and that's exactly the argument going from the automorphic side to the classical one. If you started with mi, you will, when you do inverse, you will get mi inverse on the right, and that still gives you the same thing. So that's the main idea that was there, exactly as in our exercise on self-adjointness of the Hecke operator. Okay, so now I'm going to replace this line here by theorem. Well, I want to do a number 8, and I'm going to write down number 8 just because I am morally obligated to do that, but I'm not going to tell you what it is. Well, that's not a nice thing to say, right? But let us see what I'm writing down. Phi is annihilated by, you see, let me explain, okay? One thing we have not used at all so far. Can you tell me one thing that we haven't used? Exactly, brilliant. We did all of this thing and the f need not be holomorphic at all. So what does it mean by being a holomorphic function? Cauchy-Riemann equations, right? These are these differential operators. Now classically these are the differential operators, but you can reinterpret them as elements of the Lie algebra of GL2 acting on functions on the group. So differential operators acting on functions on complex upper half plane gets translated to Lie algebra elements acting on functions on the group. The Cauchy-Riemann equation corresponds to one particular guy. So Cauchy-Riemann equation, for example, you might know, corresponds to the weight lowering operator. So if you have a holomorphic Siegel modular form, you hit it by a weight lowering operator, you get 0, because that's the property of being holomorphic. The weight lowering operator is an operator in the Lie algebra, and it's what's called the minus part of the Lie algebra there. And now maybe this makes a little bit of a sense. You take your GSP2n, look at its Lie algebra, look at the complexification of the Lie algebra, write down the Karta decomposition, and then the negative roots. Basically there are positive roots and negative roots. The negative roots act, so everything acts on phi, but we want a negative roots to annihilate it. And that's the same thing as holomorphicity, Cauchy-Riemann equations. The negative roots or positive roots, all of them correspond to differential equations on the function on the Siegel upper half space, and holomorphy is vanishing with respect to these guys. So I haven't written down anything, and actually that's going to be the plan for today's lecture and the next 4. I am going to not write down any details about the Archimedean story, and the reason is that it will take me 2 lectures to set it up. So it's a lot of setup and completely disjoint from the adelic and the p-adic one. So from time to time, just for completeness, I will write down the Archimedean property that we have, but I'll kind of avoid writing down details. And maybe you have to be satisfied just by explanations of holomorphy is Cauchy-Riemann, is the same as negative roots acting on the function, and so annihilation is the same as holomorphy. So that's the story here.
Okay, could you say for maybe for GL2, give a hint on what PC minus is?
Yes, GL2, you have the, if you look at the Lie algebra of SL2R, the real Lie algebra, there are these 3 elements, right? There is this H, E, and F. And then if you look at the complexification, there is, you can define 2 operators, okay? And these 2 operators, it's just some complex linear combination of H and E and F. When you apply any one of these operators, when you act on it, it spits out the weight k as a constant. It's in the center of the algebra, so it's yes. No, it gives the weight k. It gives the weight k. The other one takes the function and moves it to a weight k plus 2 function, and the minus guy takes the function and moves it to a weight k minus 2. If you are holomorphic, you do lowering, it is 0. So that's the, so I can't write down the formula, but that's what's happening in GL2. There's only one guy in GSP4. There are 3 such negative roots. So you have to look at 3, and in fact the number of variables are much bigger. And in the very first lecture I told you that I had to use partial differential equations in one of my papers. It was basically when we were trying to find out explicit formulas for the weight k vector in a Bessel model at the Archimedean place, and this was supposed to be holomorphic. So basically we had a function in some 4 variables, and this function satisfied these 3 differential equations. So we got a system of 16 PDEs in 10 variables. Okay, these things may or may not have solutions, right? Number of variables and equations is different, but luckily they had, and it boiled down to 4 PDEs. And I'm telling this because I'm extremely proud of it, because these kinds of things I was completely out of my depth, but it's a learning experience, and that's what I started today's lecture with. Even if you are not comfortable with something and it's something completely new, learning it is very useful, because you don't know when you'll use it in the future, and for this thing, for example, you have to.
The holomorphy then only depends on the Archimedean.
Yes, exactly. So the holomorphy is the Archimedean story, and the Hecke thing at a prime p is the p-adic story. All of it together is the automorphy. The automorphy is the first condition out there. Yeah.
So you're talking about GK module?
Yes. That's why I'm not talking about Archimedean, because I have to talk about GK modules in that case. Yeah. So I'm kind of avoiding that. So we have done quite a bit of analysis to figure out what properties this function has. We're going to go to the next step now. So what we are going to do is we take this function, which is a function on from g of a to c, and we get new functions from it by doing a right translation by elements of g of a. So you got g in GA gives you a new function which takes x to p of gx. The opposite, right? Right translation. The x is the variable xg. Of course, I can do this for any g in GA, but as soon as I do it, I am certainly not getting functions which satisfy these properties, because now on the right I am messing things up. But I get a whole big family of functions, and on this vector space of functions, the group is acting by right translation. So you get what is called a representation of the group, and potentially it's a huge representation. So what is a representation of a group? You have a vector space, and you have a map from the group to invertible linear transformations on the vector space. So you take the whole vector space of such functions obtained by translation, and how does a element g in GA give a linear transformation? Well, you take any such function and you translate and you get a new one. That's your linear transformation. So this gives you a representation of the group, and it turns out that potentially these big representations may or may not be irreducible, because they could be extremely huge. But if you start with a Siegel modular form F, which is a Hecke eigenform at every single prime, then we were able to prove a theorem which says that the corresponding representation is irreducible. So this is not multiplicity 1 results of GLN coming into play. This is a Hecke algebra argument, and so this representation that I'm going to whatever I'm saying I'm going to write down in a minute, but I'm just getting to the next stuff here. So you get an irreducible representation, and these irreducible representation can be written down as a tensor product of local ones. So every group G of QP acts on a local vector space, and these local representations a priori could be any random infinite dimensional vector space. But it turns out that if you started with a Hecke eigenform which has certain particular Satake p parameters, there is no choice. You can actually write down exactly what this local representation is. So in preparation of doing this automorphic representation, we want to know what these local G of QP representation looks like coming from Siegel modular forms of full level. These are the spherical representations. So let us just look at that next. So now for the next maybe few minutes, I'm going to restrict to P a prime, and I'm going to look at my again GP and my KP. And basically I told you that the Hecke eigenvalues here determine the representation at P. And to figure that out, I need a very nice concrete realization of this space. The way it comes out is, turns out that you can write this as polynomial ring in n plus 1 variables. And you should remember n plus 1 is exactly the number of Satake P parameters we had. So it turns out that you can realize this in a very natural way, and so I want to tell you what that natural way is. It's called a Satake isomorphism, and that's where the name Satake comes up, from this much more general Satake isomorphism concept. So what we have is the following. So let us take Tp to be the diagonal elements in GP. So if you have a GLN, you can take arbitrary diagonal elements, but now since you have the symplectic group, the first n and the last n have to be related to each other. So this guy looks like diagonal u1 to un, and then u0 u1 inverse to u0 un inverse, ui in GL1, non-zero elements. Remember when we had in the symplectic divisor thing as well, this times this was the similitude, this times this was a similitude, so the u0 is the similitude in this case. Okay, so this is the maximal torus in the group, and in general all of these elements can be any non-zero p-adic number. We want to look at a compact subgroup, so instead of any QP cross, take units. So take T0 to be T, P is understood, so let me not carry the notation P. So this is ZP cross. So these are elements in the ring of p-adic integers whose inverses are also ring of p-adic integers. Once again, you can look at the notes where all these things are defined. So that is ZP cross. And just like we defined the Hecke algebra here with GP and TP, these were compactly supported functions on GP which were left and right KP invariant. So there is a group and a compact, and we defined the Hecke algebra of the group with respect to this compact. We can do the exact same thing here, a group and a compact, and we can define compactly supported functions on T which are left and right invariant with T0.
So there's this T0 meaning this UI is in GP cross.
Yes, exactly. The UIs are all in ZP cross. You're absolutely right. So if you had a diagonal like this, so think about it this way. So if you had A, B, CA inverse and CB inverse, so this is one of the elements in T. The function inside HTT0 is only dependent, does not matter if you have units on the right or the left, okay? Which means these numbers are p-adic numbers, but you can forget about units. So basically you can, so there is this very nice fact that any element of the p-adic numbers can be written as a power of the prime p, maybe positive or negative, times a unit. Okay? So if you are looking at the value of any function in that space on this element of T, all you care about is what power of p do you have here. You don't care about what units are going on here. So essentially you can realize that the generators of this HTT0 are precisely, so let me write down these elements first. So x0 is characteristic function of diagonal. I am going to have powers of p, so one of them corresponding to the similitude. So first n elements are units, the last n elements are p times unit, and then x1 to xn, I want the first one to be p times zp cross, all the others are ZP cross, and then if I have a P, I want it to have similitude 1, so I do a P inverse. And in this way I can go all the way to Xn. So I just mentioned that the value of a function in that Hecke algebra depends only on the P part of U1, U2, Un up to U0 or A, B and C. The first one tells you what's happening for U0, and x1 to xn tells me what power is there for U1 to Un. So basically, since we are allowed all positive as well as negative powers of P, we can see that our HTT0 is isomorphic to x0 plus minus 1, x1 plus minus 1 up to xn plus minus 1. So essentially whatever I said gives you a proof of this, which is one of your exercises. So basically you take an arbitrary element in the Hecke algebra and its value just depends on the P parts, see which P parts it is going to be, and then pick that. So if you had the first one is P to the power 5, then you will have x1 to the power 5, because that will give me P to the 5 here, and so on. So that's how you will get a polynomial in here. So it turns out that I already got you n plus 1 elements here, and these are the n plus 1 elements which are essentially going to generate my Hecke algebra H GP comma KP, and the way it's going to work out is the following. So now is the Sataki map. You take H GP comma KP, your F, and you map it to the following thing. Sataki map of F evaluated at T is, and this is the same as, so here T is in our T of QP, and delta B of an element is given by a formula which just gives you some powers of the U's, and well, it's a relatively complicated formula. So what is this function? You take this element of the Hecke algebra, so this is a function on GP. Then you get a function on TQP by first taking the absolute value to the power half of whatever this diagonal gives you, and then you integrate over n. N now in this case is the unipotent of Borel. So for genus 2 you already saw exactly what n looked like, and then you integrate this function that you started with, Tn dn, or if you wanted to change the order, then this changes by delta B to the power minus 1. So this is how the Haar measure works in this case. And what did I do? I created a C valued function on T, and now I can very easily see that if I had a unit on the left, the unit's absolute value is 1. So it doesn't, this delta B absolute value does not change. A unit on the left, but you can see that these guys are diagonal elements with unit entries. They are of course inside the big maximal compact Kp. They are inside GSP4, GSP2 and Zp. So F is left invariant under Kp. On the right you use this formula. So in fact this function does belong to this space here, and you get a very concrete formula. Not only is this guy inside this space, so this is inside H T T0, there is some more invariance going on. If I took a T and T is something like this, and I just permuted the U1s to UNs, the permutation corresponds to some Weyl group element acting. You can see that you can do an appropriate change of variable. That change of variable compensation is exactly going to come out of this, and it's going to be invariant. So it's not just a function on T, it's actually invariant under the action of the Weyl group. So Weyl group is just basically permutations of the UIs, or you replace a UI by U0 UI inverse. So in fact W is the Weyl group, and the map is your Sataki map. So of course I am going through a lot of complicated stuff to write down this thing precisely. But what I really wanted to do is, if f was actually a characteristic function of Kp m Kp, I wanted to actually write down the formula for SF. And as soon as I write down the formula, you're going to see immediately, you are going to recognize it immediately as something you have seen before. So let me write down this formula. So suppose Kp m Kp is disjoint union mi Kp, and notice what I'm doing now. I'm writing mi as ai bi p to the d I0 ai transpose inverse, where the ai is given by lower triangular matrices now, p to the di1 going to p to the dn din, and there's not here. Maybe I think maybe the bi should come here. I think on my notes the bi is on the top, but I will check and see if this is a typo. So if I look at such a double coset with these kinds of coset representatives, and I choose my f to be the characteristic function of Kp m Kp, then the formula for SF evaluated at t, or maybe I don't even need to write down the t here, because I'm going to write down SF in terms of these generators x0 to xn, and the formula is the following: p to the delta n plus 1 by 4 x0 to the delta summation over I product j equals 1 to n p to the minus j xj dij, where delta is valuation of mu of n. So in lecture 3 we did Hecke theory, and we defined the Satake p parameters as the complex numbers alpha 0 p to alpha n p, which miraculously satisfied lambda of g, the Hecke eigenvalue, is equal to some summation product blah 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 with the alphas coming in here and the exponents coming from the decomposition and so on. So you, in that classical setting, you could actually give a proof of that formula, but now with this kind of a connection here, this is exactly the counterpart of that formula that we had earlier. So this is actually going to give us the Satake p parameters as well, and that's the exact connection that we're going to have right here. And this was actually the reason why I went through the Satake map, because this is a very standard thing that you do for various different scenarios with various different groups, and although it gets a bit complicated here, you exactly see the n plus 1 generators. The definition of this map is a little bit complicated, but very naturally it gives you a by T0 invariant function, and as soon as you write down a characteristic function of a double coset and its single coset decomposition, this part here pops out. So actually I was in the earlier version, I had made this into exercise. I had broken it down into 2-3 different exercises, but then the number of exercises went up to 12 or something, so I thought, well, let us not overload with exercises. Maybe one thing I should say, that a lot of things that I'm talking here, this theorem as well as this Satake, etc., there is a fantastic reference that many of these things is coming out of. This is a paper of Mahdi Asghari and Ralph Schmidt. They have maybe 2 or 3 papers together, and this one is called Siegel modular forms and associated representation. So they do this classical to adelic transfer and all of these things in full detail. So the proofs of things that I've left out are completely explicitly given in that paper, but we don't have enough time to go through that.
That's also the title of this course.
That's also the title of this course, yeah. One possibility could have been to just take that paper and spend 2 weeks on it, but then Ralph, I had asked him once, and he said he is actually a representation theorist, and I personally believe that I am more of a number theorist. So it's just semantics, but then the focus sometimes changes. So I would personally like to spend 5 lectures on the classical Siegel modular forms, because that's where number theory in a certain sense lives. Given a choice, Ralph would spend all 10 lectures on just the representation theory. But yes, this is a very good reference. So as soon as we have something like this, we have a connection between classical Sataki P parameters and something on the p-adic setting, and now I can write down our spherical representations. So these are bread and butter of local components of automorphic representations. There is a very standard way that they look like. It's very explicit, and a lot of things are known about them. And if you are looking at Siegel modular forms of full level, for every prime you get exactly those spherical representations. So let us see what these representations look like. So this is still for a finite prime. So finite prime is still what's going on. We haven't gone to the global case yet. So spherical representation. So basically we have vector space V and a representation pi of G of QP. So this is an infinite dimensional vector space, and pi gives a map from G of QP to invertible maps on V. So that's what a representation is. And we have to put some adjectives on it. It's smooth and admissible. So some nice properties which make this into a good category of representations. And we call such a representation is called spherical if it contains a non-zero vector V fixed by, so maybe called V0, fixed by Kp, i.e. I take this vector in the vector space, I apply the linear transformation corresponding to Kp, I get the same vector for all Kp in Kp. Okay, so this is called the spherical vector as well. We will think about it later, but representations which have these nice fixed vectors are very convenient. If you want to do any kind of analysis out of it and you say, oh, let me pick a nice canonical vector out of this representation, there is a spherical vector. You might ask, what if I have more than one? It turns out if the representation is irreducible, then there's only one up to a scalar, so there's also no choice, it's a nice canonical one. You can normalize it some way. So these are very nice guys, and here I wrote this down as some infinite dimensional vector space, but we have a very concrete realization of these guys as c-valued functions of GP. So that's the reason why these representations are nice. We know exactly how they look like. So how do you construct such a representation? You take characters chi0, chi1 up to chi-n from Qp cross to C, which are unramified. So this is important. This means that chi x z is equal to chi of x for all units. So it's trivial on units. So remember, Qp cross was power sub prime cross Zp cross. So if you want an unramified character, you know it's trivial on this, because it's a character, a power of p gets the same value as chi of p raised to that power. So any of these characters are completely determined by its value on p. So one single complex number gives you one unramified character. So you take n plus 1 of these, and you can define a character on the Borel. So Borel is b equals Tn. So n is the unipotent that we saw earlier, T is the torus of diagonal guys, and you define a character chi from B to C. So this is trivial on the n part, and chi of diagonal u1 to un, u0 ui 1 inverse to u0 un inverse. Well, you see exactly n plus 1 elements of Qp cross. So you apply these n plus 1 characters on it. So this is product chi I ui, I equals 0 to n. So this gives you a character on this big thing. So the big Borel, which is like this upper triangular matrices, you say that on the diagonal you give these values, off diagonal ignore it. So it's well defined and everything, and then you construct what is called as the induced representation. So the notation is the following, and I'll tell you concretely what this is. This is the induced representation, and what is this guy? This is the space of all smooth c-valued functions on GP, such that if you take any element G and you multiply on the left by an element in the Borel, then this character pops out. So character, and to make everything unitary, etc., we also do this delta b to the half. I need absolute value, right? Am I missing the absolute value? Of course. To the half f of g for all b in B and g in G. So this is an infinite dimensional vector space. You can come up with infinitely many such functions. All of them, if you take linear combinations, you get other functions like this, and your group acts on this once again by right translation. If you multiply by any of these functions on the right, this property on the left is not messed with. So you get this guy. So this, your group GP acts on it by right translation. So once again, we had unramified characters which were completely determined by a complex number, and out of that character we constructed this big infinite dimensional vector space. And now the question is it irreducible or not? There are some criteria you can figure out on chi-i's to tell you irreducibility, but no matter what, it is known that every such big representation has a unique constituent which is spherical. So has a unique constituent which is spherical, and we can denote this by pi equals pi chi 0 chi 1 to chi n. So this is how you can construct infinitely many spherical representations, and the fact is that every spherical representation is obtained this way. So when I said you know everything about these representations, at least the way it can be constructed is not a lie. So you know exactly how this looks like.
Can you please explain that delta factor?
Delta was defined
Put in there.
to get unitary actually. So delta b to the half you put in there, then the representation is unitarizable. So that's the reason you put in the delta b. So it's called normalized induction. You can define it without the thing, it's still a spherical representation. But
You start with every time that induced representation is unitary. Is that what you're saying?
yes, so if I have unramified characters and I define it this way, this is a unitarized. So I can come up with a yes, exactly. So that's the idea.
Don't you want to start with a character which is unitary?
Yes, so unitarizable is when your characters are unitary. So there are some criteria. So not necessarily the characters don't necessarily have to be unitary, but there are some, depending on the group and the thing, there are some criteria. Yeah. So unitarizable is if the data that you are inducing from also has to satisfy certain conditions. But without the delta b, then it does not work at all. Yeah. But the characters are unitary implies representation is unitary. Maybe it's not as simple as that. There are more cases where you still get unitarizable, but there's a different constellation of characters. Maybe the chi's are related amongst themselves. So on Monday, when we look at local representations of GSP4, we'll actually look at a big table at all possible chi's that you can have, and then there is a criteria for being unitary as well. We'll look at that too.
And when you meant unique constituent, you mean a sub-representation?
Yes, so it's a sub-representation, yeah.
In general, it need not be.
Yeah, so it's either a quotient or a constituent, yeah.
The Jordan-Holder decomposition.
Yes.
It's a quotient, right?
It's a sub-quotient.
Yeah, it's a sub-quotient usually, yeah, that's right. Okay, so I am almost out of time, and so what I'm going to do is, I'm going to tell you the two punchlines. The first punchline is very good visual picture of how these things look like. So spherical representations, this are one-to-one correspondence with unramified characters, and you have to mod out the action of the Weyl group. We already said that the unramified characters are completely determined by n plus 1 complex numbers. Well, again, so C cross and these guys. Now, if you have a spherical representation, then the spherical vector is k invariant. So when the Hecke algebra acts on it, it spits out a scalar, because the Hecke algebra keeps the spherical vector once again spherical, and we just said it's unique. So if you apply the operator and get another spherical vector, it has to be a constant times the original one. So you get a map, a homomorphism from the Hecke algebra to C by just action on the spherical vector. And we already saw this connection here, and this connection is just coming from HGPKP being the W invariant elements of HTT0, which was exactly this polynomial thing. So, spherical representations are completely determined by, well, there is a very nice picture to go around. You can think of it in terms of Hickey algebra, in terms of unramified characters, or a bunch of complex numbers. Okay, so basically if I take my chi I p's to be equal to bi, then I can define my local L functions now. This is standard inverse, this is product. So 1 minus p inverse product I equals 1 to n, 1 minus bi p to the minus s, 1 minus bi inverse p to the minus s, and I can define my pin L function out of these guys, and this is k equals 0 to n, 1 less than or equal to I1, ik less than or equal to n of 1 minus bi1 to bik p to the minus s. So, one of the exercises that we have is how are these bi's which come from these characters related to the classical Satake parameters. It turns out that b1 through bn is the same as alpha 1 to alpha n, and b0 is a power of p times alpha 0. So, they are very closely related. So, what we defined here is essentially the p part of the standard and spin L function, but maybe because of the power of p there is a shift, okay, in the s. So, that is going to be one of our exercises, and let me write down the final theorem. Let f in Sk gamma n be a Hecke eigenform. Let phi f be the corresponding function on GA. Let V sub f be the space generated by translates of phi f. Then pi f Vf representation of GA on Vf is a cuspidal, automorphic, irreducible representation. All these representations are tensor products of local representations, and for every finite prime p, it is one of these spherical guys. So, if p is finite, then pi p is spherical with characters, unramified characters. Chi I given by chi 0 of p is p to the n, n plus 1 over 4 minus nk by 2 alpha 0 p, and chi I of p equals alpha I p for all I equals 1 to n. So, as soon as I know my Satake p parameters, I know the characters, I know the spherical representation, and at infinity this is a holomorphic discrete series with lowest weight. In this case, the weights are given by n tuples of integers, and in this case it is just k. You could have different ones. So, last part, of course, we have not talked about the Archimedean representations, but that just is in. So, I know I went several minutes over time, but stopping without writing down the theorem made no sense. So, I apologize for going over time, but this is a place where I wanted to get to today, and this is a very good place to stop and take a breath. So, we did a lot today, a lot of things to look through in the notes. All the initial exercises are written down so as to make you comfortable with all of these adelic things and so on. So, patiently try to do them. In the afternoon, we will spend a lot of time in all of those exercises.
Are these notions defined for non-quasi-split case?
These L functions?
When you don't have a hyperspecial point, then how do you?
Yes, so very good question. So, we defined this only for spherical representations, and if you don't have spherical representation, if you don't have a vector which is invariant under this, one generally does not know how to define these local L factors. The only way you would do it is you have a local Langlands into GLN, and then you use Langlands classification for GLN to define the L function. So, if you started with a Siegel modular form with level, for primes dividing the level, it is kind of dicey how to define the L function. GSP4 you can, because now we know local Langlands for that, but in general it is not so easy. Okay. So, yeah, this is very much spherical. This is all like full degree, right, 2n plus 1, and this If you have level, then they are smaller thing. For example, it's supercuspidal, it's expected to be 1.
Yeah, when you cannot have when you don't have torus but just a minimal level, then you don't have Satake parameter.
Exactly right. So this Satake and everything is, this is a nice story. Remember I said last week that I'm looking at SK gamma n. So I'm kind of staying away from level as much as possible, but just giving hints of what happens at the level. For the local representations of GSP4, we will talk a little bit about the level thing as well, because there is a lot known there. But in general, whenever your prime does not divide the level, you have a very nice story. And prime divides the level, there are only finitely many primes. For gamma n, all the primes are away from the level because level is 1. So everything looks like this. So that is why you get a complete description for every single prime and infinity.
For those primes dividing it, we have ramified characters.
It is possible that the local representation is an induced one, in which case it's induced from ramified characters. It may not be induced from the Borel though, it might be induced from some other parabolics. So it may not be just coming from a character, but representations. For example, in GSP4, if you look at the Siegel parabolic, you had this 1x01. The levy is the 1 here, it's a GL2. So you have to start putting in, you could put a complicated representation of GL2 and induce it and get something. So,
And those correspond to the other part of the cusp forms. Right? You have cusp form and you have the full space of modular forms. And there is some remaining thing here.
so you mean what about non-cuspidal automorphic representation, or what about if I start with MK or something? Yeah, you could do that and then you don't get cuspidal representation. Either it's a global induce or it's a residual, or so there are all these adjectives that you can put in, but I'm just concentrating on the cuspidal one here.